Before we get into the details of light and other electromagnetic waves, let's recap mechanical waves. Mechanical waves require a medium. They must have matter to go through, so they can go through a solid, liquid, or gas, but they cannot go through the vacuum of outer space. If there's no medium, there can't be a mechanical wave. The speed of mechanical waves depends on the type of wave and on properties of the medium. Mechanical waves can be longitudinal or transverse. Longitudinal waves, including sound waves, have particles that move parallel to the wave energy. Transverse waves, like the stadium wave, have particles that move perpendicular to the wave energy. Remember, waves transport energy, not matter. Electromagnetic waves still transport energy, but unlike mechanical waves, they can travel through the vacuum of outer space because they don't require a medium. They basically bring their own medium, but that's another discussion for another day. Speed of electromagnetic waves depends on properties of the medium, if it's in a medium, and the frequency. Yes, I know I said before that frequency doesn't affect wave speed, and for mechanical waves that's true. But electromagnetic waves are different, so when we talk about them, we've got to talk about frequency. The speed is not dramatically different, but it will be different. All electromagnetic waves are transverse waves. The electromagnetic spectrum describes the wavelength, frequency, and energy of all electromagnetic waves. Traditionally, it's drawn from low frequency to high frequency, as shown here. Remember that frequency and wavelength are inversely proportional. So if the frequency is low, the wavelength will be long. This is the radio waves side of the spectrum. Low frequency, long wavelength. As you go up the spectrum, the frequency increases and the wavelengths get shorter. Energy is directly proportional to frequency, so if the frequency is high, like for gamma rays, the waves will have lots of energy. Remember the order of the spectrum: radio waves, microwaves, infrared waves, visible light, ultraviolet rays, X-rays, and gamma rays. The last three, UV, X-rays, and gamma, have enough energy that they can damage your cells, from sunburns all the way up to cancer. Please note that within the visible light range is our familiar Roy G. Biv color spectrum. All frequencies of the electromagnetic spectrum, which I'm going to call light because it's quicker, travel at the same speed while in a vacuum. This is the constant c and is written as 3 × 10⁸ meters per second, or, for those of you who don't like scientific notation, 3 with 8 zeros after it, or 300 million meters per second. Light is fast. Speed for electromagnetic waves gets slower as molecules block the motion. The tighter the molecules are packed together, the slower the wave will travel. So light travels fastest in a vacuum, where no molecules get in the way, slower in a gas, slower still in a liquid, and slowest in a solid, since there are a lot of molecules in the way. When a wave enters a new medium at an angle, the first edge of the wave slows down, then the next part, until the entire wave ends up turned in a different direction. Refraction is this change of direction of a wave when it enters a new medium at an angle, which is caused by a change of the wave's speed. In this animation, white light, which is a combination of all frequencies, hits a glass prism. Because different frequencies of light have different speeds, the light rays split up into our rainbow. From top to bottom, we have Roy G. Biv. The higher the frequency, the more refraction will occur, so violet light refracts the most, and red light refracts the least. Fun fact, if there's a double rainbow, the one on the bottom looks like this one, but the rainbow above it would be reversed with red on the bottom and violet at the top. To describe how much a ray of light will refract in a medium, we use the index of refraction, n. This index of refraction represents the ratio of the speed of light in a vacuum, c, divided by the speed of light in a particular medium, represented by v. The higher the index of refraction, the slower the speed. We could rearrange this equation to state that the speed of light in a medium is equal to the speed of light in a vacuum divided by the index of refraction. In variable form, v equals c over n. We can calculate how much a wave will refract, or the index of refraction of a new medium, by using Snell's law. The ray that enters a medium is called the incident ray, and the ray that bends through the new medium is called the refracted ray. We measure our angles from the normal, which is this imaginary line perpendicular to the medium boundary. Snell's law states that the index of refraction for the first medium, multiplied by the sine of the angle of incidence, is equal to the index of refraction of the second medium multiplied by the sine of the angle of refraction, or, in variables, n1 times sine of theta 1 equals n2 times sine of theta 2. Here's an example of Snell's law. The white medium is our first medium, so 30 degrees is theta 1. This means that our theta 2 is 19.5 degrees. If we plug into Snell's law, we see that n1 sine theta 1 equals n2 sine theta 2, so 1 times sine of 30 equals n2 sine of 19.5. Sine of 30 is 0.5, 1 times 0.5 is 0.5, sine of 19.5 is 0.333. Divide both sides by 0.333 and you get that n2 is equal to 1.5. The last thing I want to talk about is total internal reflection. Total internal reflection occurs under specific circumstances when light would normally refract. In these pictures you can see examples of total internal reflection, including underwater reflection, fun with lasers, and, most importantly to a lot of us, fiber optic cables. Normally, light will refract from one medium into another, like from water into air, as shown here. However, when you reach the critical angle, all of the light will refract so much that it travels across the surface instead of passing through the new medium. Once your angle of incidence is greater than this critical angle, all light will reflect instead of refracting. The index of refraction for the first medium must be greater than that of the second medium for this to happen. So n1 must be greater than n2. In this simulation, you can see that as the angle of incidence increases, the angle of refraction also increases until you reach the critical angle, where the angle of refraction is 90 degrees. After the critical angle, all light will reflect instead of refracting. We'll talk more about reflection in the next part of our unit.